No, it's 8:30:17 right now, so I'm a little late. But hey guys, good morning. We'll go ahead and get started. Can everyone hear me okay? Or I feel like I have to kneel down, but is there a way to turn this mic up a little bit?
You're good.
I can give you a handheld as well if you'd like. It's up to you.
As long as this is okay. Okay, perfect. All right, we'll go ahead and get started. So I'm gonna try to cram like a bunch of information into like 20 minutes, and then we're gonna have some good time for questions. I think a lot of the content that we're gonna go over is gonna spark a lot of questions, so I wanna leave a little bit instead of me talking the whole time. So I'm Joe, founder of VOXO, and VOXO was founded about 7 years ago. We're a cloud communications company, desktop apps, mobile app, WebRTC. We use Astricon, Camelio, RTP engine. We're going to go through some of that on the slides, but just a little bit about us. We specialize in B2B, cloud communications, contact center, chat, SMS, all the fun stuff. So we are a pretty young company. What I mean by young is I think our oldest employee is like 40, and we're, you know, a lot of us are just nerds, app developers, and you know, we just kind of have become voice engineers, I guess, over time, just learning about these different products. So I have a wife and 3 kids. I have 2 girls and a boy, 9, 5, and 2. They're sitting right up front here. So that wasn't a joke. So today we're going to be talking about scaling and managing real-time communication workloads in Kubernetes. And these are some things that we learned whenever we migrated our infrastructure from a bare metal, like co-location environment to a multi-region, single cluster Kubernetes environment in GKE. And I'm not talking about like the really hard Kubernetes where like you deploy it yourself on bare metal. I'm talking about like button mashing Kubernetes. So you guys probably know the difference. So who in here, I guess we'll start with some questions. Who is hosting in bare metal primarily? Who is hosting multi-tenant in bare metal? Okay. Who is hosting in the cloud, just single tenant, free PBX type environments in the cloud, VM? And cool. Who is hosting multi-tenant in the cloud? Okay, no bare metal. Who is hosting, the final question, Kubernetes multi-tenant hosted PBX in the cloud? No hands. Oh, wow. All right, here we go. Who wants to? Like, is this like, okay, cool. That's kind of cool. Yeah, I've always kind of wanted to. I you know, obviously Kubernetes has just so many advantages when it comes to handling failures and stuff. And those are, during this time, we're going to talk about the problems that come with, you know, migrating your kind of bare metal workloads into a Kubernetes environment and managing them and scaling them and keeping them secure. So here's our agenda. We're going to recap just for a few minutes on what we talked about last year, which is just this kind of topology of what we are talking about today, all of the infrastructure that we've deployed and that we're having to manage now. So I'll show you kind of like a graphical diagram of that, and then we're going to go into discuss the problems that we're going to solve. And then we're going to talk a little bit about the mindset shift from like this kind of bare metal, treating your servers like pets, versus the Kubernetes treating your servers like cattle mindset. And then we're going to solve those problems, hopefully, and go for questions. So real quick, this is the GitHub repo that all of the things that I'm going to talk about on this call, or on this, I don't know why I said call, is going to be available. So you can access them here at the Kubernetes repo, and you can look at our config, you can look at our Kubernetes manifest and see how we're deploying our infrastructure, and just kind of see how much we've tried to simplify it. And then this is the visual diagram of the topology graph that we're going to be discussing. This is what we have deployed in Kubernetes, and this is kind of an interactive diagram, and we'll take you to something like this. So real quick, just taking a few minutes here and going through what we are talking about during this call, and what we're talking about managing. I keep saying call. Go on a video call or something. These 3 colored boxes represent different regions in GCP primarily. Wow, I don't have, let me refresh. I don't have labels on top of some of these. Here we go. So this is a nice visual diagram that will allow you to click on each one of these nodes and get a brief description on what their responsibilities are. And you can do this later in your off time if you want, but we're going to take one of these regions and just discuss very briefly what components are in each region. So on the border, we have Camellia. Also on the border, we have RTP Engine. Inside the data centers, we have an array of Asterisk instances. These are horizontally scalable. By the way, RTP Engine is horizontally scalable as well. And then we have various other supportive applications like MySQL, Orchestrator, NAT, and just some other Node.js applications. So all of our stack, besides the 3 primary components here, is all JavaScript, Node.js, Dino, like our API and all of that. In each region, we have 1 Camellia instance. In each region, we start with 1 RTP Engine instance, and then in each region, we start with 1 Asterisk instance. And as load happens and traffic happens, the scale, each one of these components scale out except for Camellia. So as long as we have multiple Camellia instances in multiple regions, there's no issues with availability. We have we use Google load balancers to prioritize traffic to different regions based on your proximity, based on your location. And Asterisk doesn't actually have internet access. So RTP Engine takes care of the media bridging between the end client and Asterisk. And then Camellia is what directs RTP Engine and load balances to various Asterisk servers. So that's what we're talking about today. We'll move on here. Man, that's a good one. All right, so as you can see, we have very stateful workloads. This is like trying to fit kind of a circle and a triangle mentality when it comes to managing those stateful workloads globally in the very ephemeral world of Kubernetes. And what I mean is, Kubernetes needs to be able to do what it's good at, which is spin up new nodes and take nodes down. But you can't really do that with very stateful workloads without having life cycles within your applications to be able to handle those failures, handle those events from Kubernetes when it's ready to take something down or bring something new up. So we're going to talk about some of those problems and try to solve them. Like in the bare metal world, like you just kind of expect for nothing to go down. Kind of like, I guess we do, maybe you don't, but in Kubernetes, like you plan for that failure. So here are the problems. Failure is going to happen, so we have to have a mindset shift from this bare metal kind of mindset that we have into a more ever-changing environment that we find ourselves in when we use Kubernetes. So we're gonna talk about that problem, or we're gonna solve that problem. We're gonna solve the problem of dropping calls on shutdown. We're gonna do a little quick demo of how that works in a production environment. And so we don't want to drop calls. And then how do we scale? So everything is one cluster. So 3, 5, 6, 7 regions. They all need to share state. They all need to share information with one another so that we can have everything kind of talking in a single cluster, even though they're geographically separated. Maintenance downtime. We're going to talk about solving that as well. So the first problem is this mindset that we find ourselves in when we talk about bare metal versus a Kubernetes environment, and especially in the cloud. It's this pet versus cattle mindset. Like I definitely have this, this pet mentality when it comes to bare metal servers. Like you kind of know what's running on each one of them, and you're like, having to make sure that you're running certain commands on each one to perform different functionality. However, the mindset shift comes from making sure that we are allowing Kubernetes, when we migrate our workloads, do what it does best. It's very efficient in scaling your apps and moving stuff around based on CPU and node health. So kind of go into our next point here is this idea of building everything in an ephemeral way. So making apps as ephemeral as possible, designing your apps even down to your databases to a point where they should be able to sustain an outage and come back up and bootstrap themselves as a brand new node in your cluster. So we have this concept of like no PVCs, like no persistent volume claims. So everything, none of the data is persistent in our environments. Now this may be, a lot of you are probably squirming, but this is the way that we designed it. I'm not saying that it's necessarily the best way. I'm just saying that it's the way that's worked best for us. Because a lot of our larger data sets, like not our actual user data, is like offloaded to data lakes. So we can have really tiny like MySQL nodes that don't take a lot of time to bootstrap themselves when they come online. And then we also have an orchestrator example. So I don't have the actual link here, but it's available in our GitHub. You just saw our GitHub. There's an orchestrator example that we're using. Orchestrator is a MySQL orchestration tool built by OpenArch. Like GitHub uses it to manage their MySQL cluster. So we use it in our environment to manage our MySQL nodes globally in our various Kubernetes regions. And you can get some ideas from that orchestrator example about the bootstrapping nodes when they come online and gracefully shutting them down. And kind of the use of sidecar containers, which we'll talk about. And then another big component of making this all work and kind of the glue that ties what makes this possible is having kind of a global KV store where all of your services are made aware to all of your other services in a single place. And we use Console KV for that. I don't know if you guys are familiar, it's a HashiCorp product, but we use it as a global service discovery. So it's very simple to use. And then on our sidecar containers within our environment, we try to use console template, which is basically a KV watcher that updates your configs whenever Kubernetes spins up new nodes or takes pods down. We update the KV store anytime some event happens that we need to update other services. So when you're talking about bare metal, just kind of recapping here, you're probably not thinking about all these things. Like you're thinking about like persisting storage and stuff like that because you can. And you can do that in Kubernetes. You can persist storage with PVCs. We just choose not to because we want to be more flexible and be able to deploy on AWS easier and stuff like that. But so it's definitely a mindset shift when it comes from, you know, deploying in bare metal versus into a Kubernetes environment. So solving the second problem, dropping calls on shutdown. How do we prevent when Kubernetes needs to shut down an Asterisk server? How do we handle the shutdown gracefully so that we're not dropping calls? Kubernetes has the ability to dispatch events or hooks to your application, pre-stop hooks, and there's examples of that in our config, which you'll see online, that allow us in our sidecar containers to successfully dry up those Asterisk servers before Kubernetes takes them down. Therefore, we use sidecar containers for all of our primary applications. So Camelio, RTP Engine, Asterisk, MySQL, all of our kind of heavier primary applications rely on sidecar containers in order to manage the lifecycle of that primary application. And that's how we can take these events in, update the KV store, take the node down. Yep, update the KV store. So this is a very important one. Without this, I wouldn't really know how to pull this off globally. Termination grace period seconds. This is just a one-liner. By default, I think it's set to 30 seconds in Kubernetes. Whenever Kubernetes wants to shut a node down, it's going to go down by default in 30 seconds. So we want to raise this to something like 7 hours. The nice thing is, though, when our sidecar container dries up that Asterisk instance, the node will go ahead and shut down properly. So we don't have to wait that full 7 hours and spend money on that VM all day. So the quicker we can dry it up, the better. And then after shutdown happens, we ship the logs to Loki or wherever, and we've solved this kind of stateful drop call issue when it comes to Asterisk, RTP Engine. We're doing the same thing on RTP Engine. I just use Asterisk as an example, but RTP Engine has a simple REST API, or it's not really a REST API, it's just a JSON API. And you can see how many active channels. You can disable it in Camelio. Same thing with Asterisk. We're just disabling the node in Camelio and letting it dry up. So scaling, the third problem. One key thing that we've learned that was super helpful for us is let Kubernetes do what it does best and use HPAs, which is a horizontal pod autoscaler. I don't know if you guys are familiar with that. Quick show of hands. Okay, just two. So a horizontal pod autoscaler allows you to plug in a CPU value, and Kubernetes will take care of whenever your Asterisk node consumes a certain amount of CPU, will add another pod to your Kubernetes cluster. And that could mean a new VM, or it may put the pod on based on your config on the same VM. But the horizontal pod autoscaler saves you money because it can add nodes throughout the day, and I'll show you guys a quick demo of how that works. And then at night, when traffic is a little bit more lean, it'll shave those nodes off where you're saving money. I mean, we're spending, almost nothing at night in our environment. Even though we still have call traffic, it's not as much. But as the day goes through, Kubernetes will add new nodes as load and traffic increases. And you have to tweak the pod autoscaler. There's a scale up and scale down policy that you're going to want to mess with to get that right. Setting proper CPU requests on your pods in your config, in your YAML config. All of that is available on our GitHub as well, so you'll see some examples of that. And then your application lifecycle needs to be dialed in. What I mean is your sidecar containers need to be able to handle bootstrapping themselves and their primary service and then gracefully shutting down that primary service, drying it up, or whatever it needs to do before it returns to Kubernetes to say, okay, you can take the node down. And then make small iterations and test. This is a big thing. I think, like, at least for myself, I always want to make like 4 or 5 changes because I'm impatient, and then I want to see what those changes do the next day. But we've just learned that making small changes, letting it run for a couple of days, seeing the behavior in the HPA, and just letting it, you know, it's a lot easier. You're going to break a lot less things if you do that. And then lastly, maintenance downtime. So here's how you solve maintenance downtime. You just don't have downtime. Like, I don't know about you guys, but like, I don't feel like we're not allowed to have downtime. So I think we wouldn't be here I don't know how people get away with downtime, or like even maintenance downtime. I don't think you can. Like, who's doing maintenance downtime in here currently and successfully without your customers being mad? One, yeah, like you just can't, like I just feel like you can't do it. Like you don't have the luxury of being able to do that. Whereas like if you're hosting a REST API, a very stateless application, and no knock on, you know, like API devs. I mean, we're API devs, like we get it. But like you can just restart stuff and it doesn't matter, right? Like, but you can't do that with very stateful workloads, and you can't do that especially in an RTC environment. You need to create the ability in your containers, in your sidecar applications, and your primary apps to have the ability to delete anything at any time. So if we are, you know, in our production environment, I should be able to delete a MySQL node and it shouldn't affect anything. I need to be able to delete a NAT server or an Astra server and it not really impact anything, right? So these very stateful workloads, if you build your applications in such a way that support this mindset and mentality, you'll have a lot fewer headaches when failure does happen. And then also rolling restarts. So Kubernetes has a nice way of handling rolling restarts via kubectl, or if you use something like K9s, which we use, a little CLI tool. You hit a button, Kubernetes spins up 2 or 3 new pods, and then starts gracefully shutting down your old pods. And while it's gracefully shutting down your old pods, traffic from those old pods, so any new connections that come in, go to your new pods in Kubernetes that were just spun up to replace the old ones. So use rolling restarts, it's a lifesaver for us. You don't have to manually sit there and like offload traffic individually on pods. You can just do a graceful restart and Kubernetes handles all of that for you. The use of Google's global load balancer. If Google's cloud load balancer did not exist, we would have like multiple entry points for each data center, each region for WebRTC traffic. And the Google load balancer uses Anycast IP. There's one IP, one DNS record, and that Google load balancer is going to anchor your traffic to Google's closest POP to you from a latency perspective. And then that traffic is going to traverse Google's internal network to your gear. And then QA well, test. I mean, you guys are in telecom. You're already familiar with this. I want to do questions in a second, but I want to do a quick demo of some of the things that we've talked about, and then, you know, we'll do questions. How am I on time? What time do I need to stop?
You have 20 minutes.
Oh, nice. did it. All right. So I'm gonna get one of my kids to make a call first. Let's pull in K9s. So K9s is a really cool Kubernetes CLI management tool that allows you to perform different functionality and monitoring of your Kubernetes environment. If I'm still connected, yeah, I'm on. So you can kind of see like your region up here. You can see all the pods that are running. You can look at your deployments, stuff like that. This is not like a K9s tutorial, but just so we know what we're looking at. This is an Asterisk pod, AST dash. We have a Camellia pod right here. We have 2 MySQL pods. We have a few NATS pods. NQLite is another it's a relational database that we built internally. It's also open source. Our API, Orchestrator lives in all of our regions as well. It's what manages the MySQL instances, and then ProxySQL, which updates in real time to notify like itself of the MySQL master and all of the read replicas. And then RTP engine here. So all of these components minus Camellia has a horizontal pod autoscaler set, or like the ability to scale horizontally. So I'm going to have one of my guys make a call, and what we are going to do is demonstrate how. So like we're gonna put a call up on Asterisk, and we're gonna confirm that that call is up, and then we are going to shut down that Asterisk server via like a kill command in our Kubernetes environment. So so when we go in here, we see these are just some sidecar apps, and here's our primary. So I'm just gonna shell into here and like confirm that I can't see it on my core. Okay, cool. So we have some PJ SIP channels up here. This looks like one call. Is that you? All right. So we confirm we have a call up. I'm gonna exit this, and then I'm gonna go back here, and I'm gonna Control D this Asterisk instance. So it's gonna ask me if I wanna proceed. Yep. So now this Asterisk instance is in terminating mode, and Kubernetes wants to spin up a new one because we have a minimum of 1 replica. And so it's always trying to keep that 1 replica online. So I'm gonna go into here, and I'm gonna look, and we can tell that this is not actually down yet. It's in terminating state. So at this point, we can look at our sidecar app, and we can see that there's a 5-second polling via the Asterisk API to see what channels, if we have any channels up. We can see that we have 2 channels active. And if we scroll up, maybe a little bit further. Up a little bit further, we disabled this Asterisk instance in our global KV store, and we also disabled it in dispatcher via Camellia. So this server is not allowed to take any new calls. So we can see here, oh, did you hang up?
It went down.
Oh, dude. All right. So this server is down now. So it went down as soon as the call hung up. Our 5-second poller continued to run, and on the next iteration of that poller, we noticed that there was no calls on it, and the node went down. You can see the node uptime here is like just a few seconds, I guess. So this is the one that Kubernetes replaced with the one that went down. This one can take traffic now, like you can make another call. We could do the same exact thing again if you wanted to. Let's do that really quick. This is gonna be a lot faster. Like make another call.
Let me know when you're up.
Yeah, we're up. They're up.
What's it doing? Okay, so we're gonna kill this. So now we have this pod trying to come up right here as soon as this one goes terminating. So you can see that poller running every 5 seconds. Now you can go ahead and end your call. Okay, cool, so we're done. We sent the kill signal like course stop now to Asterisk, and we killed all of our sidecar containers, we shipped our logs, and we've successfully not dropped any calls. This pod is now dead. And we have this other Asterisk server online here ready to take calls. So over the span of a day, we have Kubernetes has the ability to start up new Asterisk servers based on load and shut them down based on traffic. So just showing you that real quick here. So this is like production traffic in one of the like low volume regions. You can see that there's only one Asterisk server currently online. These are the calls. And these are how many active calls currently. So in the next, I don't know, couple of hour or so, Kubernetes is going to want to add another Asterisk server to handle the load. I'm just going to go to like the past 4 hours. Can't see that. A second. Okay, here we go. So this is like yesterday. So you can see here that we started with one minimum replica of one single Asterisk server. And as the calls ran up here to around the 200 mark, the CPU also hit a point where the horizontal pod autoscaler needed to create a new node. And you can see here where this new node comes online, this yellow one, and it starts taking calls immediately. And you can see the green node start to kind of taper off right here and go right in line with the yellow node. So Camelio is load balancing calls between the two very efficiently. And we're handling all customers' traffic. Like this is not just a single customer, this is like all customers that would be in this region at this given time. And then towards the end of the day, you can see here that the CPU kind of tapers off to a healthy point, and Kubernetes removes this node, and at this point, this yellow node, and at this point, you can see the calls start to taper off and dry up successfully. So we didn't drop any calls here, just waited for them to dry up and told Camellia not to send any new calls to it at this time. And then now we're back to one instance, and it's saving money. So yeah, questions? And that's it. A lot of stuff, yeah.
For Orchestrator, is there something similar for Postgres that you've used?
We just use MySQL and SQLite. We haven't messed with Postgres, but I don't know how that would work. I think Postgres has some stuff. Good question. I don't know. That's my answer.
Do you use master database?
Single master. Yep. So an orchestrator takes care of selecting the new master, and we can do like a plan failover if we want to as well. So like, just show you I'm not gonna orchestrator, so I'm just gonna forward a port and access orchestrator in my
So here's orchestrator, here's the primary node currently, and here's all the read replicas in these various regions right here. And so at any point, I could drag this node on top of this one and make it the master if I was like doing some maintenance in the data center or whatever. All of this that makes this work and like bootstrapping MySQL nodes and all that is available on our GitHub. I think we have an orchestrator repo. Another question.
All nodes have the RTP engine driver, kernel driver.
The what? The what driver?
Kernel driver for RTP engine. The kernel driver to handle media.
I have a kernel driver for RTP engine.
Oh yeah, the kernel driver, yeah. So we use the in-kernel packet forwarding in GKE. So thankfully, GKE allows us to use the Ubuntu nodes. And the Ubuntu nodes, I think, are 22.04. And in our GitHub, our RTP engine sidecar script, just a bash script, it will take care of installing the DKMS, the RTP engine kernel module on that node whenever RTP engine comes online for the first time. So we do all of the transcoding and all that in the kernel. On GKE, like normally you would, but yeah, it's nice that it works. You get way more performance that way. Yep.
Maybe more of a Google question, but if you're using UDP, how do you guarantee the packet's always going to hit the same place?
If you're using UDP, how do you guarantee that all the packets are going to hit the same place? So what we use for traditional SIP devices is DNS SRV records because we can't rely on the Google Cloud Load Balancer for UDP traffic. So we use the Google Cloud Load Balancer for TCP and HTTP traffic, like WebRTC. But we use Google's DNS, which now supports cloud. It's called DNS SRV geolocation. So if you make a DNS SRV request from Atlanta, the records that your phone, that your SIP phone gets back is maybe different than the records that I would get back if I was in New York. The priorities are gonna be different. And it's cool they support that now, so we can anchor those registrations to the closest Camelio instance. And we don't forward our registrations to Asterisk. Asterisk just handles invites for us. So the endpoints register to Camelio, and we don't even use like AORs like for individual endpoints. We just use a single PJSIP endpoint in our Asterisk config. And we handle all of the other routing via SIP headers and Camelio. Yep.
Do you concentrate all customers or all calls from one customers on one asterisk, or do you spread them around?
They get spread between all asterisk instances. So Camelio has the ability to route to any asterisk instance in any region. However, it's going to prioritize the local region that it's in because that's where the customer is anchored.
So do you do transfer?
Yes. Yeah. So we use. Yeah. Exactly. So we do transfer, but that was a pretty big project for us, like call pickup and transfer. So we use NATs as a message bus and persistent store to update all of our microservices or what we call presence inside of our infrastructure so that each asterisk instance has access to the present state and the channels, the asterisk channels that all endpoints have up or ringing or whatever. So that's how we can handle call pickup. So we can make that query to the presence app. It has the channel. We can go from one asterisk instance to another to bridge the call or to transfer or to handle like an attended transfer or call pickup. I don't know if that answered the question, but yeah, next.
Have you looked at all the different public cloud solutions and compared the level of Kubernetes support across them? And then chosen Google? I'm assuming you're using Google, right?
Yep, so the question is, have we compared other cloud providers, Kubernetes stack to each other? Yes, we did. We found Google much easier to use and feel like it supported the latest versions of Kubernetes quicker than the rest. And we had to do way less work in plumbing between regions like in VPCs, because with Google, you just have one VPC and all of your regions are automatically connected to one another. And with RTP and SIP, like you don't need like IP masquerading and stuff. Like all of your IPs need to be able to contact each other directly. So that's why we chose Google. Simplicity. It had the plumbing set up in the VPC by default already. And it was super nice using gcloud to put together one script to deploy a new region. So we can run one script and have a brand new region up online, connected to our global cluster in a matter of 15 or 20 minutes. Yep.
During startup or tear down of an Asterisk, do you configure the dispatcher set right on time, or are they all pre-configured within the KamaIDIO?
Do we configure what? The PJ SIP config?
No, the KamaIDIO dispatcher set.
Yep. So good question. So do we configure the KamaIDIO dispatcher set when a new Astricon node comes online, or is it pre-configured? It is configured whenever the Astra server comes online. So when the Astra server comes online, we use dispatcher in MySQL, and it writes the record to, it actually writes an item to the KV store, and console template, which runs on each KamaIDIO instance, reads that in real time. That watcher reads it in real time and updates KamaIDIO via RPC and updates the database. So basically we save the state to KamaIDIO via the reload RPC command every time a new Astra server comes online or goes down. So we're resaving the whole state globally every time a new one comes online or goes offline. So it should be very dynamic, and there's no preloading pre-config. Yep.
So for those Asterisk containers, is it the sidecar that's updating console KV whenever a new one comes up?
You got it.
Okay.
Exactly. And that's why it's so important for us to have these sidecar containers on all of our apps, so they can manage that life cycle of updating the KV, taking it down, because console template is awesome. You can also set up your own HTTP watcher with like a Node app or something, and anytime that KV store changes, globally all of your apps are aware of that change. It's so nice. I mean, it's an absolute lifesaver. Any other cool questions?
I just wanted to get you to put your GitHub stuff up in the front.
Yeah.
Again.
Yeah, for sure. So this is our, I don't know if you guys can see this, but our GitHub is VOXO. So if you just go here, you'll see all of our open source projects, some of them not open source, but just give me a shout and we don't mind sharing. Does that help?
Yeah, I didn't know, you had a second page of them that you have where you had your visual part, is that?
Oh, yeah.
Is that in
So
here?
that's actually, I think you can click on it right here.
Okay, I just didn't know how that, I didn't catch that part of it.
Yeah, I didn't go over that. Yeah. So real quick.
You had the QR code.
Yeah.
But I didn't get
There
a
we go.
chance to get the info.
So just copy down that link
Because I don't know if that visual diagram works on mobile, but there's a little tiny link there you can copy down. Yeah.
Thanks.
So you mentioned Amazon at one point, but you're doing everything in Google Cloud?
Yeah, in various Google Cloud regions. So that diagram shows you all the regions, and we'll be on AWS eventually, but like this is working for us now. Yeah, it's a different animal. Yep.
Have you thought about doing bare metal yourselves and going back to the data centers?
Just when we break big stuff, that thought crosses my mind sometimes. like when you know, migrating customer and something breaks, like let's just let's abort. But we've stuck with the plan, and it's worked out. We have production traffic in Kubernetes, and it's Kubernetes loves real-time communication.
Let me be clear, I meant running Kubernetes.
Oh, no way, no, never, that has not crossed my mind. We, yeah, that's a different animal too. I don't know, you may have better experience. Are we coming up on time?
Yeah, technically you went over, but it's fine.
Oh, dude, sorry.
You're over by 1 minute.
Okay, can I take Fred's question?
Yes, of course, it's Fred.
Any kind of information you have about how many calls, let's say, you're running on each node or anything like that?
Yeah, Asterisk is really happy with no more than about 200 calls per instance. RTP Engine doesn't care about 1,000 calls within kernel packet forwarding. Camellia, we don't know. We haven't hit any limits there. CPU, the CPU loves Camellia. Asterisk, the CPU doesn't like transcoding. After we got rid of transcoding in Asterisk and offloaded it to RTP Engine, and also like recording, processing, and stuff like that, we saw significant CPU decreases. And we're running tiny VMs in Kubernetes. So we don't want to run like these really large VMs and try to put like 1,000 calls on Astra servers. We'd rather have like 200 or 300 calls at most on an Astra server. That way you're minimizing the blast radius of some things.
Thank you.
Mm-hmm.
What size nodes are you running?
The 4-core VMs. Yep, 4-core, the compute optimized ones. Yeah, they love 200 calls. 300, 400, they load average starts to spike and stuff. But yeah, we've done lots of optimizations in our environment to improve CPU spikes and stuff like that. So if you're having issues with that, we probably run into it. Yep. Sorry about that. We're done. Thank you guys.